Hey everybody, today we're going to be talking about really intuition behind dropout regularization. If you've seen the previous regularization and overfitting video, you remember that we had really a cost function, and the cost function was equal to y hat minus y squared, and then what we did to to minimize overfitting or implement regularization, if you remember, we had weights equal to the initial weights, and these are vectors, minus a learning rate times the gradient of the cost function, plus we had this regularization term, and we used something called lambda, which we could set as a hyperparameter divided by the number of neurons in the network, and we did the sum of L equal 1 to L, and that L being the total number of layers. And we, if you remember correctly, L1 normalization is the weights, all of the weights, and then L2, L1 normalization is just the absolute value, and then L2 normalization or regularization is the weights squared. And so we, just to remind you what regularization was, is that we were adding this term here to create, to really minimize overfitting. And that's the purpose of regularization, is to reduce overfitting. Well, dropout is another technique, and you can think of it here, and let's just, so our nomenclature is consistent, let me make this y hat. So what we're doing, if you think of this as if we have some inputs, and then this is our layers of our neural net, we have layer 0, 1, and 2, and then we have an output. And I've drawn it in a slightly different way. You see neural networks represented this way, as well as from left to right. And I've typically used left to right in the past. And what I've got on the right here is that there has been dropout. And the intuition behind dropout is that if I remove a few of the neurons, I have to spread, really spread out, it spreads out the weights and between the other neurons. And you can kind of think of it like a sports team, as if you've got a sports team, a basketball team with 5 players, and you lose your forward and your your point guard, then you have to, the rest of the team has to take on the burden of replacing them, and so other people on the team have to pick up their expertise. So that's kind of the intuition behind this, is that you can drop out neurons. And then the other intuition is, if you remember back to our model of if we went from a high order polynomial to a lower order polynomial, then often we reduced our overfitting. So dropout reduces overfitting, and that is the objective, overfitting. Dropout reduces overfitting, and that's a regularization technique. So you can say in layer 2 here, we had a 50% dropout, and then 3 out of 5 would be 60% in layer 1, and so forth. So another concept here is that if we added, well, let's just go ahead and add to layer 1 another node here. And so it had more neurons in layer 1 than in layer 2. A question becomes, layer 1 is more likely to overfit, so you might want to have a higher dropout rate in the layer that may have the highest tendency to overfit. And you can do that within the Keras library, the Keras functions that we'll use, and I'll show you how to do that in just a second. So this is basically, this layer has 50%, this had 60%, and if we added a couple of more neurons here and we dropped one of those out, then what is that? Let's make sure that we do this, that we have what, 3 out of 7, that's, yeah, if you 16% times 3 is about 48% dropout rate here. So that you prescribe this as a hyperparameter, which is your dropout rate. And so this is your dropout rate. And so 50% of that layer will be dropped out. So those are some high-level things to conceptually kind of understand what happens. Now, when you implement this in a Keras model, what happens is that each of these neurons on each epoch, and we haven't really talked about an epoch, you input your samples, you train, and then you randomly select another set of samples from your training set, and then the next iteration or next epoch, your dropout will randomly select. So you can think of this layer randomly selecting, roughly 50% of the neurons in that layer would drop out each time. And you may have a dropout rate that for just a layer with few neurons that may be a low dropout rate of 10 or 20%, and a layer with a high number of neurons may have a 70 or 80% dropout rate. And so each epoch, the neurons are randomly selected that will be dropped out. So that's something to be aware of. So this is a regularization technique. And if we applied this to our handwriting, the MNIST data set, so here's a 5, and here's how it would look in your Keras model. So you start out with this is your sequential model. This flatten basically takes this 28 by 28 and reduces it to one long vector. So you have one long vector, it's been flattened out. And then the next layer, this dense layer, is a layer of 128 neurons. And then notice on the next line there in the model is a dropout rate of 50%. And so of that dense layer on each epoch, and if you're training, you may do 10 to, let's say 10 to 100 epochs, and it draws randomly from your training set, a batch from your training set, and then 50% of the neurons on that dense layer will be dropped out. So this is preventing the overfitting. And then some of the language that we've used before, the next thing is an activation, which is a ReLU activation, a dense layer, then another dropout, and so forth. Now notice we have 10 of these numbers. We have 10 numbers. So the last output is 10, and then softmax, which we've covered before as a type of activation function, which will give you basically the probability of each of the 10 elements. Each one, what's the highest probability, and we'll select the highest probability as the output. So here is softmax. So this gives you an idea of how you would implement dropout for each layer. This number could range from 10 to 80%. You can experiment with that, and then also shows you how you would start putting this together in a Keras TensorFlow model. All right, that's all I had for today. A quick overview of how to use dropout.